Hello and welcome to another exciting lecture for Foundations of Behavioral Neuroscience. In this lecture, we will be talking about the neurotransmitter system. So first, let's talk about the number of neurotransmitters. Now, there are at least dozens of different ones. There are likely actually over 100. So good luck knowing them all. And realistically, though, we're only going to focus on these 7. The glutamate, GABA, acetylcholine, dopamine, norepinephrine, serotonin, and endorphins. So let's start with glutamate. So glutamate is basically the best way to explain it is it's the major excitatory neurotransmitter. So when we talked about what goes on with neurons and neuron firing, you've got some things that excite or increase firing. You've got some things that inhibit. So glutamate is the one that's going to increase firing. It is essentially the major excitatory neurotransmitter in the body, and mainly in the brain, and it's responsible for most of the time when you're looking at excitation. Some things that it's directly related to are learning and memory and synaptic plasticity, and overactivation of glutamate can result in seizures because the glutamate basically causes non-stop firing. If it's excitatory, if it increases firing, if an overactivation of glutamate occurs, then what you end up getting is seizures because there's too much activation. They act in 3 main ways on ionotropic receptors. There's the NMDA receptors, the AMPA receptors, and the Cannabinoid receptors. We'll look at these a little bit, but we're not gonna. We'll look at least the NMDA one, but we're not gonna go into it too much beyond that. So the ionotropic that we've got here is going to refer to the ones that open up or relate to ion channels. So they increase ion channel activation, whether it's direct or indirect, because there's, again, multiple of these, direct or indirect. On the other hand, there's also metabotropic glutamate receptors, and these are the ones that increase things like metabolism of the breakdown of neurotransmitters in the synaptic gap. The one we are going to talk about, the NMDA receptor drugs, or the NMDA receptors for glutamate, is going to be the ones where it is a non-competitive antagonist. If you'll recall from before, what does that mean? Non-competitive means it doesn't act directly on the receptor site. It acts on a different place on the ion channel. Specifically, this one is one where it'll go into the ion channel and block the ion channel. So it is an antagonist, meaning it blocks the ions from going through. And specifically, we've got PCP here, well-known drug, and this one blocks the ion channel, so ions don't go through it. And actually, when it blocks this ion channel, it in a sense changes the firing rate. Another one that's related is ketamine, and it is sometimes used for treatment of depression. It's actually been found more and more to be highly effective for treating depression. But this is another non-competitive antagonist, so non-competitive antagonist that also blocks the channels. It just doesn't block it to the same degree that PCP does. So it does some of the same effects of PCP, but it doesn't have as strong of a hallucinogenic effect as a result. So you get it is all in ways, this is an anesthetic. It reduces pain. Okay, the next neurotransmitter we'll talk about here is GABA. Gamma amino butyric acid, and it is whereas glutamate is the major excitatory neurotransmitter, GABA is the major inhibitory neurotransmitter. It tends to inhibit firing. It's highly associated with anxiety, sleep, and memory. And there's a couple main that we'll look at. We'll look at just A, but there's GABA A receptor, which is ionotropic. Just like with glutamate, ionotropic is going to result in affecting the ion channels. And then there is GABA B receptor. There's actually more than just these two, but these are the main two. And this is just like the previous one. It's metabotropic. It's going to result in things with metabolism. But the one we're going to look at here is A. So with GABA A, we've got things like benzos. So benzodiazepines, if I can say it, which is mainly used to treat anxiety. And this is also an indirect agonist, or this is not an indirect antagonist. This one is an indirect agonist that is going to basically, it binds to another part of the receptor, and it actually, the GABA is there. The benzos basically bind to a different part of the ion channel and enhance binding efficiency of GABA, so GABA is more likely to bind here when the benzo is bound. So this is things like Valium and Xanax. Another one is the barbiturates, mainly used to treat seizures, but it does a similar thing, but to a lesser extent, in that it's, again, an indirect agonist. It's now over here. It is believed to be the same site that alcohol binds to. But a lot of things here, and this is important to note, a lot of things about this we don't know for certain. We don't know for sure. That's why when I said we know of dozens of neurotransmitters and there's probably over 100, that's because we don't know all of them. There's actually new science coming out every year that's discovering new things relating to this. Some of this stuff, some of these main things we know now, we didn't even know 10 years ago. So it is a rapidly developing field. Now we've got acetylcholine. This is one relating to neuromuscular function and cognitive function. So the ones that are going to be relating to this is things like nicotine. So there's a receptor that's called the nicotine receptor. It's where nicotine binds. However, it isn't only nicotine that binds to it. So this one is one of those that was newly discovered, and it was discovered that nicotine binds to it. Turns out they found out other things bind to it after that, but because the first thing they found that bound to it was nicotine, then, or the chemical involved in nicotine, is in it. Because of that, they named it the nicotinic. This one's ionotropic as well. It affects ions and ion functioning, or ion channel functioning. So nicotine itself is a direct agonist in that it binds to these ionotropic receptor sites directly. That's where direct comes in, and it increases the activation of that channel. There's also another one for acetylcholine that is a competitive antagonist, meaning it is something that competes for sites, and it competes for sites and reduces functioning. And there's a couple others we've got here. We're not going to go into these too much, but basically these are different ones that are used to, sometimes they're used to treat diseases, sometimes they actually create various different functions like nicotine does. This last one is actually used in treatment of Alzheimer's. So it's an indirect agonist that prevents the metabolism of acetylcholine. The thing that I want to get to here is, well, there's a lot of different, well, acetylcholine is one specific, I would say, type of neurotransmitter. There's a lot of different subcategories within that. The next one we're going to talk about is dopamine. And so dopamine, there's three major pathways of brain pathways of dopamine. There's the nigrostriatal, there is striatal, I cannot speak today, sorry. There's the mesolimbic, and then there's the mesocortical. So the nigrostriatal is basically a part that regulates motor coordination. So it's motor. The mesolimbic is one that regulates pleasure. And one thing here is increased activity is related to schizophrenia. So remember how before I talked about how dopamine, if you get an imbalance of dopamine, you actually can have schizophrenia-like symptoms. Well, it's because, again, this pathway is associated with schizophrenia. And then there's the mesocortical, and this one is where you get higher cognitive functioning, and attention. Now, so these three major dopamine pathways, one's for motor coordination, one's for pleasure, and one's for cognitive functioning and attention. So you can see here some of the things that comes with various different dopamine drugs. They can increase pleasure, they can possibly relate to motor coordination, and they can relate to cognitive functioning and attention. So let's look at some of these. Some of the competitive antagonists is things like a lot of different drugs that are out there, especially early drugs that affected behavior, pain, things like that. These were the competitive antagonists. You also have the major ones that you might recognize more, which is the indirect agonists. So let's talk about these for a minute. The indirect agonists are going to affect these dopamine pathways in basically a way where they're going to in a way shut down these pathways or reduce them. And that's where you get things like where certain amphetamines like Adderall or certain stimulants like Adderall. Adderall isn't directly an amphetamine, it's a stimulant. Certain stimulants like Adderall can then have an effect on cognitive functioning and attention. One of the things that's believed is that ADHD is due to improper balance in pathways of the dopamine pathway. And Adderall, being an indirect agonist, basically increases that dopamine pathway. By increasing that dopamine pathway, it regulates it such that people with ADHD then have a better ability to focus their attention. Amphetamine and cocaine on the other hand, yeah, I can say cocaine. Amphetamines and cocaine on the other hand, these are ones that are strong stimulants that are going to do things like, and again, going back to that, we've got the motor coordination that's there, pleasure, but just the higher cognitive functioning. That's why these are typically used for people who are doing things where they need that higher cognitive functioning and abused in that way. So when we're talking about some of these dopamine pathways, it's why these work the way they do, because the dopamine drugs, many of the stimulants, affect the pathways that are related to things like pleasure, attention, focus, and muscle coordination. I'm not going to spend too much time on this slide, but the point is when it comes to Adderall, there is strong evidence that the use of Adderall is appropriate in situations where you've got individuals with ADHD, if the person is properly diagnosed. So if you take a abnormal psychology class, you'll find out that there's a lot of misdiagnosis of ADHD. ADHD has overlap with a lot of other disorders. So things like a sleeping disorder, so someone who has sleep apnea and isn't getting a full night's sleep, they will have issues with things like attention and focus and hyperactivity. So someone who has a sleeping disorder might get misdiagnosed with ADHD. If you give that person with the sleeping disorder Adderall, it's going to have an adverse effect on them. If you give somebody with ADHD Adderall, though, it tends to have a focusing effect because it's, again, regulating that pathway. It's proven through study after study that Adderall, Ritalin, these various different types of stimulants with people who actually have ADHD, that it is beneficial. However, when we talked about one of the things we talked about was tolerance. Adderall being a stimulant, people build up tolerance to it. So you have to keep increasing the dosage, and it can become harmful if you increase it too much. This leads us to the other side of it. So there's the fact of abuse of Adderall due to its reported effects of being able to increase focus and things like that. However, that the thing is, and we'll talk about this on the next slide, it does not have the same effect for those who do not have ADHD. So even though it does increase focus, attention, things like that in those with ADHD, it doesn't necessarily with those who don't have. So let's look at a couple slides relating to that. First, let's look at non-medical stimulant use. One of the most common reported uses for stimulants, non-medical use of stimulants, is academic purposes. So there's a self-report that it increases grades, and so people believe that it increases grades. 75% of people here believe that it increased grades. There's up here reasons for medication misuse: improving study skills, focusing on a test, staying awake. So there's a strong lean towards use for focusing, staying awake, studying, and a belief that it increases grades. The question, though, becomes, does it actually increase grades? So one of the things they did a study with amphetamine salts. So this isn't Adderall itself, this is amphetamine salts, but they have essentially the same effect. And there was no correlation found between the perceived benefits of the salts and actual performance. Basically, a placebo was better than the use of amphetamine salts and Adderall in these different studies that have been done. So placebo effect is greater than the actual effect of Adderall. So for those who are using it for non-medical reasons, for those who don't have ADHD, it doesn't increase word recall. It doesn't help recognize figures. It doesn't help with the Raven progression matrices in learning. So for all of these, it does not increase over a placebo the effect of these. Even more, we can look at the effects of non-medical use of stimulants on grades. For college GPA, Non-users, it's a 2.96 on average. All non-medical users, it's a 2.74. It's actually lower. If we look at what is used, stimulants only, analgesics, stimulants and analgesics, all of those, every single one, the 2.82, the 2.71, the 2.61, all of those are below the average college GPA. Granted, this is a study is going to be correlational in nature. There has been causal studies that have been done where researchers got approval to give stimulants to and those control, as we saw in the previous one. And the plain and simple fact is that stimulants do not, in those who do not have ADHD, stimulants do not increase grades, do not increase learning. I'm not saying don't do drugs. I'm not going to be the person who's going to get up here and say don't do drugs. I'm going to say if you're using stimulants like Adderall to increase focus, to increase studying, to increase your grades, unless you've actually got ADHD, it's not actually doing that. So why are our stimulants so addictive, and why are stimulants so abused? Besides just this perception of a benefit that is not supported by the science, well, stimulants activate the mesolimbic dopamine system. This is the system responsible for reinforcement and reward and pleasure. So if it's the system responsible for pleasure, it increases pleasure, which is a reward in it of itself. Even if you're not aware that it's rewarding itself. So because of that reinforcement and reward system, people become addicted. And 11.3 to 18.5% of adults initiating treatment with stimulants were later diagnosed with a substance use disorder. So those taking stimulants, there is a good chance that they are later going to develop a substance use disorder. So this is another reason to not use stimulants unless you've actually been diagnosed. Again, I'm not up here preaching don't do drugs. I'm up here telling you the effects and the negative side effects as well as the lack of benefits. How about some of the harmful effects? So certain amphetamines can cause amphetamine psychosis when used for prolonged periods of time at sufficient quantities, especially if you're not getting enough sleep. It can actually lead to paranoid psychotic behavior. That's one of the biggest ones. So a paranoid belief that people are out to get you. This is very similar to some of the symptoms of schizophrenia. So when we talk about schizophrenia later in the semester, we'll look at some of these things about how a lot of these different drug systems, a lot of these different neurotransmitters being out of whack actually can lead to same symptoms as schizophrenia. So this paranoid psychotic behavior, this irrational belief that people are out to get you, again, is one of the positive symptoms of schizophrenia. And positive doesn't mean good. Positive means it's a active thing. And chronic amphetamine use, especially if you're not getting enough sleep, can basically cause too much activation of the mesolimbic dopamine pathways, which can be associated with, again, these positive symptoms of schizophrenia. Also, prescription stimulants, they've been associated with an increase in onset psychosis. So things like Adderall, the amphetamines, especially the amphetamine stimulants, not the non-amphetamine stimulants like Ritalin, but the amphetamine stimulants, they are more associated with this increased risk of psychosis. So again, it's another reason to not abuse Adderall. Let's switch to another neurotransmitter now. Now we're going to look at norepinephrine, also called noradrenaline, because noradrenaline, if I can say it right. Sorry, I'm having so much trouble. I still have a slightly stuffy nose, so some of this talking is difficult. So norepinephrine is related to adrenaline. Interestingly enough, it's also related to dopamine because it's synthesized from dopamine. The body first creates dopamine, and then that dopamine is broken down into norepinephrine. And this one's main thing that it does, the main thing norepinephrine does, is increase sympathetic nervous system activity. This is where that adrenaline comes in. When you get adrenaline, it's because of the increased sympathetic nervous system activity. Adrenaline being released into the body gets you ready for that fight, flight, or freeze. Decreased levels also are known to be related to depression. It may cause it. It may be the causal goes in the other way, but it's correlated with depression. And it's believed to be responsible for regulating attention as well, just like norepinephrine is. Let's look at some of the noradrenergic. I cannot say that. The norepinephrine drugs. So the main one that you might have heard of is serotonin norepinephrine reuptake inhibitor. So it's similar in ways to SSRIs. These are SNRIs, serotonin norepinephrine reuptake inhibitors. So in a minute when we talk about serotonin, we'll talk about SSRIs. But this is an indirect agonist. Again, it's indirect, meaning it doesn't bind directly to the binding sites. It binds to other sites, and it blocks reuptake of serotonin and norepinephrine. So it's going to basically block the reuptake. And this is mainly used for depression, just like SSRIs are. So its main use is for treating major depression. Another one that is here is Receptor, and this is another indirect agonist, but this one blocks just norepinephrine reuptake, not serotonin and norepinephrine. And this one's actually used to treat ADHD because by blocking norepinephrine reuptake, it actually indirectly results in effects on the dopamine pathways. So you can see how all of these kind of are interrelated, and changes to one can cause changes to another. Another one that's a direct agonist results in a decreased release of norepinephrine, and in this one it's basically going to result in lower firing. Next one we're looking at is serotonin. So serotonin is the drug that's mostly responsible for regulating mood and sleep. Also, it's called 5-HT. In just a second, we'll look at things like 5-HTP, which is a synthetic drug that you can take that mimics serotonin. But this is synthesized from tryptophan, and basically results in more drowsiness. It can be metabolized by oxidase into 5-HIAA, which is again related to some of these things. So by having serotonin and metabolizing it, it results in other transmitters. And as I already said, it regulates mood and sleep. Serotonin drugs, the biggest one being SSRI, selective serotonin reuptake inhibitor. It's an agonist because it blocks reuptake of serotonin specifically, and this is used to treat depression and anxiety because it reduces those firings that result in these cycles of depression and anxiety. So this is where you get Prozac, Zoloft, things like that. There's other serotonin drugs that are not, unlike the previous one where they're indirect agonists, these are direct agonists. They're going to mimic serotonin, and this is where you get things like LSD and shrooms. Interestingly enough, there's been a lot of evidence lately that shows that shrooms is very effective in treatment of depression. So it's especially in other types of treatment-resistant depression. There's this mounting evidence that shrooms actually is responsible for a sizable reduction in depression in some individuals. Another serotonin drug is ecstasy. So this one's another agonist, but it's another indirect agonist, and it basically enhances release and blocks reuptake of serotonin. So there's just a flood of serotonin going on. There's more being released. There's less being reuptake. So it can result in hallucinogens, neurotoxic effects, and it results in some interesting side effects from that, like reductions in thirst. That's why people using ecstasy are more likely to die of thirst than they are, or die of dehydration, sorry, than they are of many other of the drug's effects, because it reduces your thirst. However, there is some positive effects that have been found from MDMA, and that is those with chronic PTSD are actually showing improvements in their PTSD scores. They're showing a reduction in PTSD after the use of ecstasy. So it's one of those that like a lot of these, they have multiple effects. And if an addiction doesn't occur when used in moderation, things like that, they can definitely have some positive effects on various different things, especially things that maybe are part of those pathways. So the serotonin pathways, PTSD is known to have some, or the serotonin pathways are known to have some effect on PTSD. So changing up those pathways can possibly change the effect on PTSD. Let's look at that in a graphic. So ecstasy neurotoxicity, you get ecstasy that's going to block the reuptake and enhances the release of serotonin. So the ecstasy comes in, it blocks reuptake and enhances release, so you get essentially overfiring. And this is where the neurotoxicity can come in. So the second stage of ecstasy neurotoxicity is where MAOs come in and essentially they deplete the serotonin. So nothing's been reuptake, there's been a rapid release, so there isn't as much serotonin in the gap anymore, there isn't as much serotonin in the presynaptic membrane. And what ends up resulting here then is that once serotonin is depleted, the dopamine instead is taken back up in by the serotonin transporter into the serotonin neuron. The dopamine there is then converted into hydrogen peroxide by the serotonin neurons, resulting in toxicity. One of the things, though, that can be done here is a way to block that, a way to block the dopamine from being pulled back in. So something like Prozac. Prozac will block the dopamine from being pulled back in. It can't be pulled back in. Then, as a result, the toxicity does not occur. Next, let's look at the endorphins. And actually, when we're talking about endorphins, we're not just talking about endorphins. We're talking about endorphins and enkephalins, which are very similar in that they basically do the same thing. So when we're talking about these, we're gonna look at these as endorphins, but really there's enkephalins, there's dynorphins, there's all these different ones that that do a similar thing. So the most common endorphins are opioids, and we have endogenous opioids, and specifically endogenous opioids are ones that are produced in the brain and have multiple actions throughout the body. So these are ones that are produced in the brain and body, and these aren't ones that are basically produced in drugs outside the body and taken in. These are produced by the body. Like this first one, the mu opioid receptors, these are result in pleasure, but also in respiratory depression. So when you get other things that mimic this, so you can get other opioids that come from outside the body that mimic this, and these will result in these types of things like pleasure and as well as the respiratory depression. The enkephalins, it's another one with analgesia, and then the final one, dynorphins, I cannot speak today, are relating to things like dysphoria and stress, as well as the analgesia. So then let's look at some of those opioid drugs, the ones that are from outside the body that have an effect on these receptors we were just talking about. Some of the main ones are things that the ones you know: morphine, heroin, fentanyl, oxycodone, methadone. These bind mainly to the mu opioid receptors, and they mimic these endorphins. So they lessen pain, that's the analgesia, the analgesic effects. They increase pleasure. However, the side effects again is a respiratory depression, so the possibility of basically an overdose killing you. Interestingly enough, and you've been seeing some of these in pictures, but interestingly enough, 120 years ago, 100 years ago, heroin was prescribed just like aspirin. So it's then, and early on, morphines were overprescribed. The toothache syrup had these types of things in it, so giving these types of drugs to kids. There are, though, competitive antagonists to these direct agonists, and these are ones you should be able to recognize, at least the first one as well, and that's Narcan. Narcan basically blocks the mu receptors, and because it blocks the mu receptors, the mu opioid receptors, even if you've got these direct agonists here in your system, the Narcan blocks it, and those cannot bind to the mu opioid receptors, the agonists, the morphine, the heroin, all of those, and as a result, you don't get the overdose because the Narcan blocks them. That's why if you know anybody who you even suspect is abusing opioids, I recommend having Narcan on hand, and it on a regular basis. I see it about once every 2 years. Pharmacies give away Narcan, so you can get that and just have it on hand just in case. It's better to have it and not need it than need it and not have it. Another one of these systems to look at is the cannabinoid system, and this is essentially a neuromodulator that works with cannabis to modulate the functions of glutamate, GABA, dopamine, norepinephrine, serotonin, opioids. It modulates all of those. And the main receptor is CB1, and CB1 is the one that cannabis, weed, the component of that, which is THC. Let's switch the slide. So you've got THC. THC is a direct agonist in the cannabinoid receptors. It's high in psychoactive effects, and it affects all those other systems like we talked about on the previous one. Another thing that so that's a direct agonist, THC. An indirect agonist is actually CBD. So this is where CBDs and CBD oils come in. Because it's an indirect agonist, it prevents the metabolism of basically the thing that's affecting these receptors. So it itself is not psychoactive, but when it is burned, it is converted to THC. That's why if you can use cannabis oil and not have the psychoactive effects here, but if you burn it, you get the psychoactive effects. It is possible, it's believed now, to be converted into THC in the intestines. So if CBD is eaten, it is believed to basically convert it. And it works in vitro as well. So what exactly is going on here? Well, CB1 receptors are actually on the presynaptic terminal. So they are on the terminal that releases the neurotransmitters into the synaptic gap. Activation actually inhibits that G protein signal that we talked about a couple weeks ago, resulting in a suppression in neurotransmitter release. So by the binding here, it suppresses release, so not as much is released, and results in influences on perception, appetite, pain, nausea, motor coordination, and memory, because neurotransmitter release from the presynaptic terminal is reduced. Let's look at it though from a drug standpoint. So is marijuana, is weed, a gateway drug? Well, 80% of cocaine users started out with marijuana. So 80%, that's pretty high. This is the Special Action Office for Drug Abuse Prevention talks about this. How 80% of cocaine users started out with marijuana. I bet 80% of cocaine users, actually probably 100% of cocaine users drank water. Oh, wait. It's when you're looking at this, you can't draw causal explanations from just these statements. You actually have to look at other things. Long-term studies of high school students' patterns of drug use show that most young people who use other drugs have tried marijuana, alcohol, or tobacco first. That being said, many people who use weed do not go on to use other drugs. So it's not a guarantee that you're going to go on to others. It's more of it's considered a gateway drug only because of its ease of getting and its ubiquity of use. I don't know how it is now, but I know that when I was a senior in high school, it surprised me how many people I ended up seeing that I ended up smoking weed with. It just surprised me with that, because there was a lot of people that I thought were just like too good to do that, and then you go to a party and you fire one up, and the people just show up out of the woodwork, coming from everywhere. It's because it's pretty ubiquitous, the use now, especially as it's becoming more legal. This was even before it was legal, but now that it's becoming more legal, its use is becoming even more ubiquitous. That being said, there are bad or negatives to the increased use of marijuana. So one of the things is more people are driving under the influence of weed. We've already got a problem with people driving under the influence of alcohol. The issue is that more and more people are now driving under the influence of marijuana, and performance tested in a simulator actually shows that being high on weed has just as deleterious of effect, if not more of a deleterious effect, as alcohol. Because one of the biggest things is reaction time. Reaction time is very hindered with the use of weed, and this reaction time is very important when driving. How many times are you driving and you know that just, if you hadn't reacted as fast as you did, you would have been in an accident? That can happen multiple times a day sometimes. And now imagine having that slower reaction time. It can be really bad. So they looked at it again in simulators, finding that it impaired driving. It's similar effects of alcohol. In some ways, it's worse, and definitely there's an additive effect of the two. And here's a way to show that out, that traffic deaths related to marijuana in Colorado. So you've got the number of deaths, and basically relating to when legalization occurred. So commercialization occurred here, and it started rising from there. It was already rising, but it started rising from there. There was a small dip on legalization, but now you see in the 4 years after legalization, and again, this is about a 4-year-old study, but even within 4 years after legalization, you've got 2 to 3 times as many traffic deaths related to marijuana. So again, I'm not going to be the person who's up here telling you do drugs, don't do drugs, but I will be the person who's up here telling you don't do drugs and drive. Don't drink and drive. You are putting yourself at risk, but you're not only putting yourself at risk, you're putting other people at risk. So even if you don't care about yourself, or you think you're bulletproof, you think you're immune, think about that other person who's driving down the street with their kids in the back seat, that your lack of attention, focus, and reaction time causes her to get in an accident, and you end up killing her or her kids. So definitely, I will never be the one up here telling you don't do drugs. I'll be up here telling you the negative side effects of drugs, but I'm not going to be the one up here telling you don't do drugs. I will be the one up here telling you don't do drugs and drive. Don't drink alcohol and drive. It's just not worth it. Relatively short lecture. I shortened it up a bit because of the way I was feeling. We talked about the different neurotransmitters, acetylcholine, glutamate, GABA, dopamine, norepinephrine, serotonin, and then we finished up with the endorphins and the endorphin-related ones. Thanks. Come on back.